Jennifer Bowman. I work at the Voinovich School of Leadership and Public Affairs at Ohio University, and I'm a senior project manager with our Energy Environment team. Today I'm going to talk with you about a study called the Preliminary Assessment of Polychlorinated Biphenyls, Congeners, R-chlors, dioxins, and furans in the sediment and soils at the U.S. Department of Energy's Portsmouth Gaseous Diffusion Plant in Piketon, Ohio. And you can see our contributing authors to this study. This is a two-part study. The first part, we characterized the PCBs, dioxins, furans, congeners in the soil and stream sediments along the Little Beaver Creek, which is the north drainage on the Portsmouth Gaseous Diffusion Plant, and near the switchyard X533. While this also was providing a validation and verification for the development of the expedited fields survey method and sampling techniques for measuring PCBs, congeners, dioxins in the sediment and soils, which leads to the part two of the study that Dr. Glenn Jackson is speaking about, which is the development of that mobile unit to detect PCB congeners and dioxins on site to optimize the assessment and remediation decisions on the ground that reduces the overall cost. So our study area, the Ports plant, is located in Pike County, Piketon, Ohio. This plant was constructed from 1952 to 1956. Its primary use was to enrich uranium to be used for military and then later commercial reactors. In 2001, it was put in cold standby, and then later in 2005, full cold shutdown, which is the precursor step to the D&D activities, the decommissioning and decontaminations. In 2010, that award for the D&D work was given to Fluor, B&W, Portsmouth, to carry out those activities. Polychlorinated biphenyls are man-made chemicals that have been in existence since 1929. They're widely used in industrial and commercial applications because of their chemical properties of non-flammable, they're chemically stable, they have the high electrical insulating properties. And because of this, PCBs are stable and they're persistent in the environment. Manufacturing of PCBs stopped in 1977, and their use was banned in the United States in 1979. PCBs absorb strongly to organic matter. They're lithophilic and they bioaccumulate in the environment. So these different degrees of chlorination of the polychlorinated structure are called congeners. And our study looked at the PCBs, congeners, dioxins, and furans on the site. So there's 12 dioxin-like PCBs, congeners, and they're shown here. These show their toxic equivalent factor, the TEF value. So for example, PCB 118 is 30,000 times less toxic than the most toxic dioxin, which is TCDD. So we always compare the PCB congeners' relative toxicity to TCDD, being the most toxic dioxin out there. So even though these are dioxin in nature, they're much more toxic than the other 209 PCB congeners. This set is elevated to a set of its own that shows that these are more dioxin-like, more toxic than the other PCBs. So we focused on this set of congeners when we did our analysis to see if these types of PCBs were in the environment. Okay, R-chlors. R-chlors are typical. It's a name. It's a trade name for a mixture of PCBs. So you often will talk about R-chlors, 1254, 1260. These two in particular was a mixture of R-chlors that were used on site at ports, and we used we looked at total R-chlors, 1254, 1260, and the others shown there in the graph. Okay, dioxins and furans. PCDs, PCDFs, they're made up of a family of polychlorinated dioxins and furans. The source of PCDDs and PCDFs in the environment is through the combustion of PCBs and the explosion of fires and transformer explosions. And so that's how they get into the environment. They're significantly more toxic than PCBs. And again, for example, OCDD, that's the octachlorodibenzo P dioxin, has a TEF value of 0.0003. Did I say that right? 0.0003, making it about 3,000 times less toxic than TCDD. So we're always comparing our dioxins, furans, and PCBs back to the most toxic dioxin, which is TCDD. So a little bit about history of PCB at ports over the past 20 years. There's been multiple environmental investigations and reports that have been conducted by DOE and the Ohio Environmental Protection Agency. A more recent study in 2007 showed that PCBs were discovered in the X533 switchyard beside the transformers and the drainage lines. And this is thus providing a continual source of PCBs into Little Beaver Creek. That's the drainage on the north side of the plant. After this discovery, in 2010, the hotspots were removed from the X533 switchyard and remediated. Also, when we look at these multiple environmental investigations that were done over the last 20 years, we look at the amount of PCBs that have accumulated in the tissue of fish. Because PCBs do bioaccumulate in the environment, this is important to look at what amount is being uptake through our fish. So in 1989, DOE had a study that was done as part of their annual site-wide evaluation review, and there were levels in the fish tissue of 2.2 micrograms per gram. The FDA's limit on consumption of fish is 2.0 micrograms per gram. So this is over the FDA limit. In 1993, DOE had another investigation where fish tissue were examined, and the levels, highest level there was 1.7, so just below the FDA limit. And then even later in 2005, the highest level was 1.4. So you can see the trend of the accumulation in the fish is going down through time. Okay, so this brings us to the purpose of our study. OU was commissioned to make a new investigation of the site to determine if PCBs, dioxins, and furans are present in the sediment, and if so, what is their fate and degradation of these chemicals in the environment at ports. So this investigation was carried out during 2011 and 2012. OU was looking at the presence of PCBs in the environment at ports. And this was after the reclamation that was happened at the switchyard in 2010. And so what we're looking at really is what residual amount of PCBs are in the environment that are being washed away into drainage ditches and the creeks and streams on the north side. Their preliminary remediation goal, their PRG, for the cleanup that happened in the switchyard was a level of 25 parts per million. So anything that was higher than 25 parts per million in the switchyard was determined to be a hot spot. And the levels of PCBs that were found in the first top foot, the top layer in the switchyard, the highest was 1,400, so 1,400 parts per million in the switchyard. Our study looked at really what was that residual washout from years of PCB oils that were being washed out, accumulating into the environment. These are our sampling sites. We had 15 sampling sites along the 3-mile section of Little Beaver Creek, starting in the headwaters here and flowing to the northwest to the mouth of Little Beaver Creek. We also investigated the holding ponds, the X230J, located here, flowing north to Little Beaver Creek, and the X230L holding pond, located here. And the drainage ditches that drained off of the X533 switchyard in this direction and in this direction. We sampled, so at these 15 locations, we sampled the top surface, and we also sampled the subsurface at about 11 to 12 inches below the surface. So we were looking at what accumulation of PCBs are at the very surface and what is, a foot under the ground. Because of the nature of PCBs to accumulate and to absorb to organic matter, this was important to see what was at the surface and what was accumulating through time at lower levels. We had a contract laboratory that we worked with, the GEL Laboratories out of Charleston, South Carolina, who did most of our analysis, as you can see on the slide here. They had an affiliate laboratory, Cape Fear, in Wilmington, North Carolina, who handled the analysis of the PCB congeners and the dioxins and furans. We also did grain size analysis with Shaw Geotechnical Laboratory in Knoxville, Tennessee.
So I'm going to talk about the results of this field, the field characterization of PCBs and dioxins and furans on the port site. We looked at several different parameters, like Jen introduced. So what I'm going to show you is a series of different plots that are going to kind of describe the distribution and the changes of these different parameters throughout the site.
The cleanup at the port site addressed 25 parts per million, or 25,000 parts per billion. The graphs that we'll show you in this presentation are in parts per billion.
The green part of these pie charts represents the concentration in the surface of the sample, whereas the red shows the concentration in the subsurface. So part of the point of that was to look at where these chemicals were depositing and how they may change over time. So on a plot that plots mostly green, what you see is that there's a much greater concentration at the surface, and a plot that has more red shows a greater concentration at depth. So to start off, looking at this distribution of total aurochlors, so this is the total PCBs in parts per billion in these sediment samples, what you can see is that the larger bubbles, which represent a greater total concentration, are seen on the drainages coming off of the switchyard. So the switchyard is shown in the middle here, this box, and those drainages coming off of there have greater concentrations. Whereas where that remediation that Jen introduced happened in this corner of the switchyard, we see very low concentrations. Another thing to notice is that this one largest bubble doesn't have any red. That's because that sample was taken in a sediment pond, and so we only have one sample from there because it's very difficult in a pond to take a subsurface sample. So what you can see is that we do have some higher concentrations in the drainages coming off of the switchyard, and they're pretty low coming off the switchyard, or coming off the site. So one of the things about PCBs and dioxins and furans is that they tend to bind to organic matter, and they tend to bind to clays. So what we have to do when we analyze the data is look at both our total sample, but then also normalize our concentrations by total organic carbon. So what you can see in these graphs is the concentration at the surface versus concentration at 30 centimeters of depth. So that's our subsurface sample. So the first plot on the left shows the non-normalized samples, and what you can see is that we have a pretty even distribution between surface and subsurface, with a few sites showing higher concentrations at surface compared to subsurface, and a few plotting the other way. Whereas once we normalize by organic carbon, first of all, we have a big cluster at the bottom that kind of show no trend towards the surface or the subsurface, and then a couple of outliers that show much greater concentration when normalized by total organic carbon at the subsurface than the surface. So what this starts telling us is that the ones that have greatest concentration at depth are absorbing to organic carbon at depth, and so we're seeing that stronger signal. All right, so one of the interesting results we found throughout the analysis of our sediment samples was that regardless of whether we were seeing a high concentration of PCBs or a low concentration of PCBs, we saw the same signature set of about 5 PCBs, PCB congeners. So these are 105, 118, 156, 167, and 189. And so what we saw was that whether we had high concentrations at a site or low concentrations at a site, these same 5 PCBs were our strongest signals. So what you can see in these plots are an example of a low concentration site, site 10, which was a holding pond that didn't have high concentrations of PCBs in it, and site 1 in Little Beaver Creek, which had 10 times higher concentrations than that holding pond, and show that same signature set of PCBs. Just to illustrate the difference between our total aurochlor analysis and our individual congener analyses, this is the same type of bubble plot, but this time for PCB 118, which was typically our highest concentration PCB across the site. So what you can see is that, again, we've got some of these higher concentrations, larger bubbles, coming off of the east side of the switchyard, and then a few higher concentrations down towards Little Beaver Creek. Again, what you can see is that there are some sites, especially coming off the switchyard, where we have a stronger, higher concentration in the surface and the subsurface, and then downstream we see that we've got some higher concentrations in the subsurface than the surface, and we'll talk about that more in a moment. What we see in these concentrations is that fine-grained sediment, so these small clay particles, have an inverse relationship with PCB 118, 105, and 156. So the places where we see more fine-grained sediment, we see lower concentrations of those PCBs. So when we look at these, I guess the point of this is to frame all of it in terms of human health risk assessments. And so DOE uses a HHRA, or Human Health Risk Assessment, of Type 1 and Type 2 screenings. So Type 1 says that immediate action must be taken, and Type 2 is a lower threshold and says that action ought to be taken, but you don't have an immediate health risk. So for each of these, there are then different categories. So specifically, you have a resident category, which is going to be more stringent because somebody's living there. A soil to groundwater category, which is how much of that PCB or of that contaminant in the soil may end up in groundwater and therefore drinking water. There are worker categories, which again are a little bit more stringent for people who are working outside. An industrial category, and then a worker category. And for each of these, then there's a target level above which we say that there's a potential human health risk. So for the PCB analyses, what we see is that for our Type 1, so that immediate action category, we only see one exceedance of a human health risk assessment. And these highest levels were in one of the settling ponds that I'll talk about in a moment. For a Type 2, so that lower level, something ought to be done level of human health risk assessment, we have more things that exceed that. So some of our dioxins, so OCDD and HPCDD, which we see coming off of the switchyard due to fires and explosions in the 1950s. And some of our aurochlors are seen as exceedances. We look specifically at some of the dioxins and furans because they tend to be more toxic than many of the PCBs. So while we were looking at the dioxin-like PCBs, we also looked at dioxins and furans. The dioxins and furans are seen coming off of those switchyards due to fires and explosions in the 1950s. And dioxins tend to result from PCBs that burn or explode. And so what we can see again is that for this human health risk assessment, for a resident level, so that stringent level, we see several exceedances for different dioxins and furans. So just to demonstrate this a little further, OCDD is octochlorodibenzo-P-dioxin, was the most common dioxin that we saw across site. And what we see is that in that X230J settling pond, we see the highest concentrations. And then, our first site downstream in Little Beaver Creek saw a reasonable concentration, and then we had some low concentrations coming off of the west side of the switchyard. Really, that site X230J is that high concentration that will signal a human health risk. So throughout time, what we see in Little Beaver Creek from past studies and our study is that while there have been some high levels of PCBs in the sediments of Little Beaver Creek, which receives the water running off of the switchyard in question, they have been high, up between 200 and 250 parts per billion in the past, but that over time, through remedial action, those levels have tended to decrease. And the levels that we saw in our 2011-2012 fieldwork were relatively low looking across the history of the site. So, in conclusion, some of the things that we found in assessing PCBs, dioxins, and furans in the sediments of Little Beaver Creek showed that overall the PCB concentrations are pretty low. There's still a concern because they do bioaccumulate, and so there are some cleanup efforts that may be necessary to protect environmental and human health. We saw that PCBs vary with depth. When we look at those bubble charts, the difference between the concentrations at subsurface and those at surface tended to look at whether it was a depositional area or not. So whether there was slow-moving water and sediments could deposit, we saw higher concentrations at depth, whereas at higher, faster-moving water, we saw higher concentrations at the surface. We see that over time, aurochlors are decreasing in Little Beaver Creek sediments, and that the sites that were remediated recently in the X533 switchyard show very low concentrations and non-detects for PCBs and aurochlors. We do see dioxin and furans on site resulting from those switchyard fires and explosions in the 1950s. And some of these do exceed human health risk assessment levels in the X230J sediment pond. OCDD is the most widespread dioxin across the site, but it tends to be lower than some of those human health risk assessment action levels. We saw the highest concentrations of all of our compounds in the X230J settling pond, and some of those levels did exceed our human health risk assessment levels. But what that tells us is that settling pond is doing its job, that it's holding those sediments and not letting them into Little Beaver Creek. Thank you very much for listening to this. Thank you to the U.S. Department of Energy Environmental Management, Portsmouth and Paducah Project Office for supporting this work. And for any more information on this project and other projects, you can see the Ports Future website at www.portsfuture.com.